Welcome back, everybody. So I've received a lot of requests to do more videos on number theory and combinatorics. So for this month, I have picked out a topic in number theory. And it's a pretty fun one. I think you guys are going to really like this one. It's very interesting. So today, it's all about rep units, which is short for repeated units. And we're going to see exactly what that means in just a few moments. But as usual, before we get into this video, there are a few prerequisites that I want you to know of. The first being Fermat's last theorem. So, if you're not familiar with Fermat's last theorem, I would recommend first reviewing that before coming to this video. But just as a quick reminder, Fermat's last theorem says for any integer a and any prime p, relatively prime to each other, so in other words, their GCD is 1, we have this very useful formula here. It states that a to the power of p minus 1 is congruent, or congruent, however you say it, to 1 mod p. And since subtraction is totally allowed in modular arithmetic, we can subtract 1 on both sides and get this equivalent form. But these two are basically saying the same thing. So if you like to think of it as a to the power of p minus 1 is congruent to 0 mod p, there's nothing wrong with that as well. So that's the first prerequisite. And as usual, we can't forget about our proof solving methods. So the main one for today is going to be proof by contradiction. So you should be very comfortable with that as well. With that all out of the way though, let's get into it. So a rep unit, by definition, is any number that contains only the digit 1. Okay, so I'm going to write out a few examples of rep units. So the number 1 is a rep unit, and sorry, that looks a little thick, so I'm just going to make that a little thinner. Anyways, the number 1 is a rep unit. 11 is a rep unit. 111, even this big number, 111,111, because all of these numbers only contain the digit 1. So this would be their basic form. Just a bunch of 1s repeated however many times. So over here, this space is filled with just a bunch of 1s. Okay, great. And we're mainly concerned with the digit 1 repeating because when you think about it, all these other numbers that repeat, for example, if we were to have a bunch of repeating 9s, let's say, that's the same as, it can be broken down as 9 times a bunch of 1s. Similarly, if we had a bunch of 5s repeating, that's the same as 5 times a bunch of 1s. So we can see it's really helpful to study this basic form because all of these numbers over here, they're built off a bunch of repeated 1s. So it would help to study this structure. That's what we are primarily concerned with today. Now that we know what a rep unit is, I have a few important pointers before we get into the problems. So these are listed in order of importance. So starting with this first one right over here, this first property. So the first important thing to note, and don't worry about memorizing these, when we take a look at this, we'll see that it actually makes sense intuitively. So nothing to stress memorizing too much about. But anyways, the first important thing worth noting is that if we have the rep unit 1, 1, 1 repeated n times, then that is equal to 10 to the power of n minus 1 divided by 9. And the proof for that is very straightforward, so we can take a look at that. We're going to start with the right side and just rewrite the numerator as follows. So that's the same as 10 minus 1, and then we just have all of this in the middle. Again, this is like a to the n minus b to the n formula, so we're just writing it all out. And then we can see the 9's cancel, and in the end we're left with all of this on top. But if we remember our definition for what it means for 10 to be raised to some power, well then 10 to the power of n minus 1 will just be 1 followed by a bunch of zeros. Specifically, there are n minus 1 of these zeros. And then we're going to add plus 10 to the power of n minus 2. So everything has shifted over one place. Okay, as follows, and we keep doing that. 10 to the power of n minus 3. We will have n minus 3 zeros, and we keep going all the way until this final, well, there's a 10 to the power of 1, and then finally 10 to the power of 0, which is plus 1. And then when we add this all up, what we get, we just add them column-wise, okay? And there will be no carryover since it's just a bunch of zeros and ones, and in the end we get 1, 1, 1, 1, 1, dot, dot, dot. So we do get this rep unit. There are n ones, and that can be seen very easily, because if there are n minus 1 zeros over here, n minus 2 zeros over here, n minus 3 zeros over here, there's 1 0 over here, and then over here there are 0 zeros. So what we can do is we can sort of view this as a list from 0 to n minus 1, and you know that there are n numbers, not n minus 1 numbers, don't get tricked, but there are n minus 1 numbers from 0 all the way up to n minus 1, so therefore there are n copies of this one, so that's the same as the rep unit repeated n times, the nth rep unit. And what we've done over here, this going back and forth from this formula to this one, and writing everything out column-wise and summing them up, I want you to remember this strategy because it comes up quite a lot in problems, which we will see later on. Okay, so this is the first noteworthy thing I want you to keep in the back of your head. Nothing to memorize though, because as we can see, we can always just write everything out again if we ever forget. With that being said, there's another thing worth noting, but like before, it's not really anything special or anything new. It's in fact kind of obvious, but it does help to think of it in this way. So it says if we have n copies of this one, so the nth rep unit, then we can always break it off into little chunks. So it says the rep unit repeated n times is the same as if we broke it off into 1 repeating itself a times, and the rest are zeros, but then we add n minus a ones. And again, the easiest way to see this is to just write it all out and line everything up and then add them up column-wise. Because if we start off with this over here, let's just copy that. Let's say we were to add that here. So from here to here, there are a ones, and then from here to here, there are n minus a zeros. But if we were to line them up with these n minus a copies of 1, well, it should be like this. Because there are n minus a slots from here to here, so they will be filled by these n minus a ones. And now when we add everything up, again, column-wise, we just get a bunch of ones. How many ones? Well, there were a copies here, there were n minus a copies here, so overall there are a plus n minus a copies of 1, which is the same as saying there are n ones. But again, sometimes it is helpful to break this rep unit up into pieces, which we're going to see later on. Now that we have these two key facts in our toolbox, now we have an actual method for attacking these problems. So the method is going to be, a lot of times we're going to use the above two facts that I showed before, along with Fermat's little theorem and proof by contradiction. So here's the prerequisites, and we can use those to analyze divisibility problems. So we'll typically look at the equations modulo something. That might sound very, very abstract right now, but we'll see it used in the problems that follow. And the reason I leave this blank is because there's no, you don't always analyze the equations modulo something. So it really depends on the problem. So sometimes we'll be looking at it mod 4, mod 7, mod 2, mod 3. So it just depends on the problem. But what we can always do is basically use Fermat's little theorem, proof by contradiction, and some interesting key facts about rep units. So keep this method in your mind. Now, seeing as primes are, of course, the most important numbers in math, naturally we have to ask ourselves, which rep units are prime? And there's not too many of them. As you can see, I've actually written out the first 20 rep units, okay? And I've highlighted the ones that are prime. So this is the standard notation. Typically, this stands for the first rep unit, the second rep unit, and so on and so forth, the third rep unit. And I've gone ahead and highlighted the ones that are actually prime. So we can see the second rep unit, which is 2 copies of 1, which is the same as 11, is indeed a prime. But when we look at the others, remember, the third rep unit is basically 3 copies of 1, which is 111. That can actually be factored as 3 times 37. So the list goes on, and we can see it takes quite a little while until we get to the next prime, which is actually the 19th rep unit. So there are 19 copies of this one, and that is the next prime. So from the second rep unit to the 19th rep unit, there is no primes. All of these can be factored as follows. So I've just included the first 20 rep units for you for the problems that we do later, and you can always reference these if it helps. Just thought it might be something useful to you. And here's a little fun fact. So this whole discussion about rep units and which rep units are prime is actually quite a modern area of study. So we can see here Rn is prime for a few values. So 2, 19, as we just saw. If we continued a little further, we would get to 23. So that's 23 copies of 1. That is prime. But then it takes a while to get to the next one, 317. That's 317 copies of 1. So that's the next prime after 23. Then 1031. Then the gap gets really huge, 49,081 and 86,453. So that's 86,453 ones. That has been proven to be prime. And honestly, that is pretty crazy. So these last two were actually very recently proven to be prime. So our 49,081 was indeed proven to be prime on March 22nd, 2022, while our 86,453 was proven to be prime on May 15th, 2023. So you can see this is pretty recent. It's an ongoing study. And, well, these two were proven to be prime with some pretty powerful computers. So it's not exactly something that can be done by hand. So don't feel too bad if you can't prove that it's prime by hand. Somebody else has already done that for us very kindly. And even more recently, actually, as of May 2024, these two huge numbers, so that's 5 million copies of 1 and 8 million copies of 1, they are believed to be primes, but no such proof exists. And I say yet, because we might get something very soon. Who knows? I don't know. It's quite a big step to go from 86,453 to 5 million, but who knows? Maybe it can be done. But of course, these will require some very, very powerful computers as well. Anyways, I just thought I'd let you know about these fun facts just to show that it's not just for the classroom. Honestly, rep units is a pretty well-researched area in number theory as well. People are working on it all the time. So it's very, very fun. But we're not concerned with the research aspect for today. We are concerned with solving some problems. So let's get into the first one. And we're going to see this method that I talked about earlier. We're going to see it in action. Let's find out how to use it. Okay? Problem number 1. Here it is. So I would say this is your most standard type of problem for rep units. We need to show divisibility. So we need to show that 1982 divides, that's what this line means. We need to show that it divides into this huge number, a bunch of 2's repeating, and there's 1980 of them. So I hope the alarm bell is sounding off, that in order to work with rep units, everything has to be a 1. And right now we have a bunch of 2's. The thing is 1982 is divisible by 2. So showing that 1982 goes into this number is actually equivalent to showing that 991 goes into a bunch of 1s. So this number, and since we divided by 2, the number of digits did not change, so there's still 1980, but this time it's 1980 1s, not 2s. So basically, if we can show this, then we have shown that. And now, as I said before, there's not much to do right now, so perhaps it would help if we viewed this from before. This is the same as 10 to the power of 1980 minus 1 divided by 9. So now our problem has become showing that 991 goes into this number. Now, unlike before in the proof, I'm not going to break this off as 10 minus 1 times a bunch of numbers being summed, so a bunch of 10th powers being summed, because you can try that and you'll see that quickly does not go anywhere. However, so if something doesn't go anywhere, we need to change our approach. Since 1980 is even, this can actually be broken up into a difference of squares. So convince yourself that this is true. The numerator can be rewritten like this, a difference of squares. And now we have a feeling that we're going on the right track, because we need to show that 991 goes into this number, and when we look at this number, 990 and 991, they're pretty close. In fact, they're off by 1, which, off by 1, I hope you're thinking of Fermat's last theorem, because that's exactly what we need to use. Because, fun fact, 991 is prime. So we can spell that out. So since 991 is prime by Fermat's last theorem, and I'm going to shorten that as FLT, by Fermat's last theorem, we know, in fact, I'm getting a bit ahead of myself. Let's go slowly. We know that 10 to the power of 901 minus 1 is congruent to 1 mod 991. Or 991 minus 1 is 990, and we can actually move everything to one side by subtracting 1. So we know that this is congruent to 0 mod 991, and I think it's more helpful to view it in this form because that's exactly where we see it. But that's exactly what we want to show. Because if this is congruent to 0 mod 991, that means this factor here is a multiple of 991. So of course, 991 will go into it. So we can spell that out. You know, this is equivalent to saying that 991 divides itself into 10 to the power of 990 minus 1. And since that is this factor, basically we've shown 991 goes into this, which is the same as this. Okay, and that's all there is to it. We are done the first problem. So I thought that was very, very cute. You can see how everything works together. I hope you enjoyed that one. Nice little introduction problem to the rep unit. Let's see another application with question 2. So instead of proving divisibility, sometimes we can prove that certain equations do not have any integer solutions. So in this problem, we're asked to prove that this equation with this number of crazy ones, the devil's repunit, 666 copies of 1, we need to prove that does not have integer solutions. And we can tell that this is a repunit problem because we have a bunch of 1s repeating. So maybe we can use some strategies for repunits to solve this. Now the way it typically goes for problems like these is a lot of times it's going to be contradiction. It's usually very difficult to prove this directly, so a lot of times it's better to assume such an integer solution exists. So in other words, there is a group of numbers x, y, z that satisfies this equation. So we can find an x, y, z which satisfies this. I said group of numbers, but I meant, triplets. So what we're going to do is we are going to start with the right side because that's what we're more comfortable with. Let's start with the repunit. So for this, we have 666 copies of 1s. For this problem, we are going to break it up as follows. Now this may look very, very random and very confusing, but when you think about it, it really is the same as we did before. So basically all I'm doing is if you expand this out, what do you get? Really, you're just getting, so first we have 6 copies of this one, and then when we multiply this out, 111,111 times 10 to the power of 6, that is actually the same as this number from before, but we just added a bunch of zeros. And now you see why I'm doing this. So basically, we're viewing it like this. Just a bunch of 1s and zeros, and they have all shifted 6 spots. So this is going to continue all the way to the necessary number of zeros at the end, and when we add them all up, and you can verify this for yourself, when we add them up column-wise, so over here, of course, there's a bunch of zeros. Here, of course, there's a bunch of zeros. We don't see them. Bunch of zeros up here as well. It's going to be a bunch of 1s. Specifically, there will be, because we've raised it to the power of 660, there should be 666 copies of this one. So basically, we've taken this and we've broken it down into this form. And now, by definition, we know that there's 6 copies of this one over here. So this is equivalent to 10 to the power of 6 minus 1 over 9 times all of this, because this did not change. So I just want to stress that point before we continue. It's very important. I want you to get very comfortable with going back and forth between this one and this one. And I want you to go from this to its expanded form like this. Now you might say this was a very random choice to break it off anyways, but when you think about it, well, 6 does go into 666 a nice number of times, specifically 111 times. So that's where the inspiration for the solution comes from. And not only that, when we look ahead, it's because we sort of already mapped this out in our head. This factor, 10 to the 6th minus 1, looks very familiar because we know 7 is prime and we know 6 is 1 less than 7. So, therefore, by Fermat's last theorem, this is where it's used now, 10 to the 6th minus 1 is divisible by 7. And if that was a little too fast for you, let's do a little aside over here. Remember, 6 is just 7 minus 1. And when you subtract 1 from both sides, 10 to the power of 6 minus 1 is congruent to 0 mod 7, which is the same as being divisible by 7. Okay, so if we know that this factor over here is divisible by 7, it is natural to take residues modulo 7. So what that basically means is now we're going to evaluate both sides modulo 7. And the reason for that is because of this 98, which is sticking out as a sore thumb as the difficult number. If we look on the left side, there's an imaginary 1 here. 1 is a nice number, 2 is a nice number, 98 is kind of a hard number, but 98 is divisible by 7. So that is the inspiration for the solution. So let us look at this equation modulo 7. Now, if we recall from basic modular arithmetic, there's a very useful fact about squares mod 7. And it's that every square modulo 7 is congruent to either 0, 1, 2, or 4. That's it. These are the only 4 possible residues. So this will be the key to this solution. And then from here, we can extract information about x and y. Because we've already confirmed this right side is divisible by 7, so the right side is congruent to 0 mod 7. 98 is congruent to 0 mod 7, so therefore x squared plus 2y squared must be congruent to 0 mod 7. If this is 0 mod 7, this is congruent to 0 mod 7, this must be congruent to 0 mod 7. If it wasn't, then this right side would not be 0 mod 7, but we know it is 0 mod 7. Because of this, Fermat's last theorem. So let's write that out. X squared plus 2y squared must be congruent to 0 mod 7. Since 98 is congruent to 0 mod 7, and the entire rep unit on the right side, which I'm going to just write as right side, is congruent to 0 mod 7. But we can do better than this because we know that the possible residues of a square modulo are only these 4 values. So there's only one way to get a sum of 0 mod 7 just by using these 4 possible values, and the only possibility is if both x and y are congruent to 0 mod 7. And this is not exactly difficult to see. You can play around with it a bit, but just in case you're not convinced, we could even quickly make a chart. And play around with this. If, let's say, x squared is congruent to 0, y squared is congruent to 0, then 2y squared is congruent to 0 mod 7, and x squared plus 2y squared is congruent to 0 mod 7. Now we can try any other combination and we'll find it will not work. If x squared is congruent to, let's say, 0 mod 7, but this time let's take y squared is congruent to 2 mod 7. Then 2 times y squared would be congruent to 4 mod 7, and when we add them up, that is 4 mod 7. But that's not exactly what we want, because we want x squared plus 2y squared to be congruent to 0 mod 7. So you can keep playing around with this. Let's say if x squared was congruent to 2 mod 7 and y squared was congruent to 1 mod 7, well then 2y squared is congruent to 2, and once again that is 4 mod 7. That is not exactly what we want. So try all pairs if you really want to convince yourself, but in the end what you're going to find is that x squared must be congruent to 0 mod 7 and y squared must be congruent to 0 mod 7. This is the only possible way to get x squared plus 2y squared congruent to 0 mod 7. Now, if x squared is congruent to 0 mod 7, we can actually do better than that. This automatically means x must be congruent to 0 mod 7. And that means y is congruent to 0 mod 7. Because that's the only way to square this and still be 0 mod 7. 0 squared is congruent to 0 mod 7. And then from here, actually, we can even do better than this, because now that we know x is congruent to 0 mod 7 and y is congruent to 0 mod 7, that means x squared is actually congruent to 0 mod 49. So two things can be true at once. I know it looks like we went from here to here and then to here again, but basically these two statements are both true. A number is both, x squared is congruent to both 0 mod 49, which automatically means it's also congruent to 0 mod 7. That is true. So we've just sort of made a stronger claim. X squared is not only congruent to 0 mod 7, it is actually congruent to 0 mod 49 because x is congruent to 0 mod 7. So an even stronger claim, because now, and it's a similar logic for y squared, because now we will evaluate this equation over here and I'm going to erase this actually. So we want to evaluate this. Let's evaluate this mod 49 and see what happens. I'm going to add a page. So I'm going to write left-hand side. So very clearly the left-hand side is divisible by 49 because we have confirmed x squared congruent to 0 mod 49, y squared congruent to 0 mod 49, so 2y squared is still congruent to 0 mod 49, and 98, z squared is congruent to 0 mod 49. Doesn't really matter what z squared is. That's because 98 is always congruent to 0 mod 49 because it's 2 times 49. So left-hand side is indeed divisible by 49. How about the right-hand side? So the right-hand side is a little bit of a different story. So remember, the right-hand side is equivalent to this over here. And let's see what that is congruent to. Mod 49. So if you go back to all the way up here where I showed what rep unit 6 is equal to, it's equal to all of this over here. That way you don't get confused when I write this down. So 111,111 is the same as 7 times 15,873. You can go back to the chart and verify with a calculator. You're allowed a calculator. I will allow you to use a calculator. And then let's see. So we found, so 1 is always congruent to 0 mod 7. We know 10 to the power of 6 from before is congruent to 1 mod 7. Now, just as a little aside over here, 10 to the power of 6 times 2 is equal to 10 to the power of 6 squared. So therefore it would be congruent, because 10 to the power of 6 is congruent to 1 mod 7, then it would be congruent to 1 mod 7 as well. Similarly, everything is congruent to 1 mod 7. We're just raising 1 to a bunch of powers. I'm going to move this over here. And now let's take a look at what we have. This is congruent to 0 mod 7. In order to be congruent to 0 mod 49, we need another 0 mod 7 to appear somewhere in this expression. But do we have that? Let's find out. When you use a calculator, you'll find 15,873 is congruent to 4 mod 7. That is not 0 mod 7, so we still don't have that second factor of 7 yet. And what about here? We have a bunch of 1s added together. How many 1s? Well, this is 6 times 1, and this is 6 times 0, so we really have 0, 1, 2, 3, all the way to 110, so that's 111 ones over here. So their sum is 111. So this sum is 111, and when we take that mod 7, we'll find that it is congruent to 6 mod 7. So we could not get that second factor of 0 mod 7. We have a 0 mod 7 here, a 4 mod 7, and a 6 mod 7. When we multiply it out, it cannot be divisible by 49 because we do not have a second factor of 7. So the right-hand side is indeed divisible by 7, but not 49. But hang on a minute. The right-hand side and the left-hand side are set equal to each other. So on the one hand, we have one side divisible by 49. On the other, we have it not divisible by 49. So that is a bit of a problem. So the right-hand side is not divisible by 49, which is a contradiction. And since the contradiction came from assuming at the very beginning that such an integer solution exists, therefore no integer solution exists, because we have derived a contradiction. All right, you like that one? That one, I would say, was pretty tricky. And I have no idea where I'm going to put this, so I guess I'm just gonna leave it there. Hope that does not bother you guys. That was tricky. Definitely the hardest problem we do today for this lesson. Let's move on to question 3. All right, question 3 is asking us to prove that this specific rep unit, so a bunch of 1s repeated n times, is divisible by 41 if and only if n is divisible by 5. So that's a pretty interesting problem. Now, if we'll recall, we can actually go back all the way up to, let me just go all the way back to our page of prime rep units, and let's see what's going on. So we can see that the 5th rep unit, which is 1, 1, 1, 1, 1, is indeed divisible by 41. As we see, there's a factor of 41 here. We can see R10 has a factor of 41, so does R15, so it would appear that the problem is indeed correct. So let's see how we can try and prove that. So the way we're going to approach this problem is we are going to let n take on the form of 5k plus r, where r will range from anywhere in the set 0, 1, 2, 3, and 4. So r will take on one of these 5 values, and of course the goal is to show then that r actually ends up being 0, because then n will be equal to 5k, which is of course divisible by 5. So that would be just like showing that r basically cannot be equal to 1, 2, 3, or 4, because then n would not be divisible by 5. So let's see how we can do this. This means this rep unit, if I just copy over here, so a 1 that repeats itself n times can now be replaced by a 1 that repeats itself 5k times, followed by a bunch of zeros that repeats itself r times, plus a bunch of 1s repeated r times as well. So basically we've just gone ahead and split up this rep unit like we've seen many times before. So I hope you're following along, and I hope this isn't too hard to see. There are 5k copies of 1 here. There are r copies of 1 here. Remember, these r1s will line up with these r0s. So when you add everything up, you have 5k plus r ones. Excellent. And we can actually take things a step further and break this up even further, actually, into five ones. So the fifth rep unit, 11,111 times all of this stuff in the middle. And of course, we can't forget about these R1s that we're adding at the end. And I'm going to highlight this because this is a pretty big step. And if you can't follow along, that's what we're going to look at in closer detail. Okay, so for those of you who are confused how we went from here to here, because that was a pretty big leap, let's break it down in a more simple fashion. So whenever you're struggling to see the general case, always try and work with small numbers. So let's try and test small values of k. So let's take, for example, k equals 2 and see what happens. So when k equals 2, that means there's going to be 5 times 2 copies of this one. So there will be 10 copies of this one. So let me just write that out. So there will be 10 copies of this one, and we still have our R copies of 0. And I'm just going to ignore this for now. That's not really important. This is the important part, because as you can see, this part stayed the same at the end. So that's not what we're really concerned with. And now from here, we're going to do what we've seen many times before, and we are actually just going to break this number up into a sum. So what I mean by that is this number is actually the same as if we had 5 copies of 1, followed by 5 copies of this 0. Of course, we still have R copies of 0 at the end, plus 5 copies of 1, and of course we still have these R copies of 0. So I'm going to shift this down. So I want you to make sure you really see this. Do you see how we can go from here to here and vice versa? Please take a moment to just sit there and read this. Let this really get absorbed into your head that these two are actually equivalent. They're saying the same thing. And the easiest way to see that is to just add them up. We see when we add everything up by column, we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then these zeros, these R copies of zeros just add up to R copies of zeros, which is exactly what this number is. Awesome. Now from here, in order to finally get a number that looks something like this, something that resembles that, we're going to go ahead and break this number up into 2 sections as follows. So let's see what happens. Oh, I didn't know you could do that. That's much better. Let's see what happens when we look at it like this. So for now, I want you to just ignore this entire right side and just focus on the left side. So when you add that up, let's take out a common factor of 11,111 Now for the top number, there are 5 zeros, so that's times 10 to the 5th. And on the bottom number, well, there's just one copy of that 11,111. And when we write it out, 10 to the power of 5 plus 1 is the same as 10,001. Is it? Hang on. No. It is this. Yes, 100,001. Sorry. So do you see how we have gotten something like this? Keep in mind, this was just the specific case for k equals 2, but in the more arbitrary case, basically k does not have to be restricted to 2. K can be any number, and then basically all we're doing is this column-wise addition, breaking the number up and then adding them column-wise, factoring this number out, and this may look like a very random number to pull out, but as I said before, the motivation for that comes from the fact that in our chart over here, we have R5, so the fifth rep unit is equal to 41 times 271. That's going to come in very handy in the next step. So let's go back here. Now, I hope that has cleared that up. So basically, there will be, when we pull out a factor of 11,111, there will be a number that has this form. Between each one, there will be 4 zeros. Okay, just like we've shown here. 4 zeros. Now, as I said before, let's go back here to the other section. I know we've ignored this, but we can't technically ignore that anymore. So you may be wondering, what the hell happened to these guys? Well, they're still there, but keep in mind, we still have these are copies of 1 to add. So why don't we go ahead and add them up? And when we do that, this is just for the case when k equals 2, but as I said before, this can extend to a general k, and I highly recommend you to try at home. Instead of just using the k value that I provided, k equals 2, try repeating this whole process with, for example, k equals 3. Okay, just so you can really see how a number of this form comes out. Basically how we get to this step. That's very important. And now we can just add this up column-wise. Since we're adding, basically these are all grouped together because there's R copies of each. Okay, so when we line that all up, then we have plus R copies of 1. So for the case when k equals 2, indeed we get something like this. That was very, very tricky to follow along, I would say. So if you need to go ahead and rewatch that, feel free to do so. But anyways, from here, so I'm just going to copy and paste this because now we are working with this. So as I said before, the motivation for pulling out this specific rep unit, so 5 copies of 1, is because we already know that it is equal to 41 times 271. And yes, you are totally allowed to use the chart listing all prime rep units well, actually the first 20 rep units, if you remember that, at the beginning of the document. So you can pull out this very handy fact. So because this is equal to 41 times 271, let's evaluate this equation mod 41. When we do that, and I'm just going to go ahead and number this one, evaluating mod 41, we see that it is congruent to, well, that's a 0, so this entire thing is going to vanish, and in the end, all we're left with is this. Mod 41. Because, remember, 11,111 is congruent to 0 mod 41. And if we look at our chart, we know that 1, 11, 111, 1,111 are not divisible by 41. So in other words, R cannot be, as we see, 1, 2, 3, or 4. Which is exactly what we want to show. R cannot be equal to 1, 2, 3, and 4. So therefore, our original number at the start, so n copies of 1. So therefore, this number is divisible by 41 if and only if R equals 0, where, remember, n is equal to 5k plus r, as we said at the start over here. So n equals 5k plus r. R cannot be these four, therefore r has to be 0. So if r equals 0, that means n has the form of 5k plus 0, which is the same as 5k. And that is the same as saying n must be divisible by 5. All right, hope you enjoyed that one. That one, I would say, is pretty tricky though. So don't feel too bad if you couldn't get that. But I hope you were able to follow along. As I said before, please try and use a different value of k at home. And repeat this whole process, okay? Excellent. Let's get into another proof problem, which will use a very similar concept to question number 3, where I was adding things up column-wise, which is actually one of the big fundamental ideas that we've been doing all lesson, actually. So here is your problem. Try and get a crack at it. So the rep unit that repeats itself 2n times is equal to a bunch of 2's repeated n times plus a bunch of 3's repeated n times, and then we take that whole thing and square. And I would say this is the perfect example of a problem that certainly looks a lot harder than it actually is. So let's jump straight into the proof. Now the way we're going to do this is we're actually just going to directly tackle the right side and then add things up column-wise and show that it's actually the left side. So we're going to get, because intuitively, you can probably be able to tell that we have a 2 and we have a 3 squared, which is a 9. So a 2 and a 9 could make an 11, which does have a 1 somewhere in there. And of course, we might have to worry about carryover, but hopefully we'll tackle that when that comes up. So that's just the little intuitive feeling that I hope you got, but let's get into it. So we're going to focus on this number first. 2 repeated n times is the same thing as, well, 2 times 1 repeated n times. So we always like to break things up so that we see the familiar rep unit. That's nice to see. And then let's do the same for the 3. So we have 3 times n copies of 1. Remember, the number of digits did not change, but remember this whole thing is being squared. So not a whole lot we can do with this. This stays the same. But now we can actually rewrite this as 9, because that's 3 squared, times n copies of 1 squared, where we've just opened everything up. And now let's go ahead and pull out a common factor of n copies of 1, so Rn, the nth rep unit. So from our first number we have 2, and then we have 9 times, well, this whole thing was being squared, so really we have another copy of n ones inside. And this is where basic definitions will come in handy, because we can simplify on the inside. Remember, by definition, 1 that repeats itself n times is equivalent to 10 to the power of n minus 1 over 9. And the reason we think to do this is because of this 9 over here, which is giving us a lot of motivation, because now we can cancel these out, like so. So what are we left with? Let's take a look. So we still have this on the outside as usual. And then let's keep the 10 to the n. But now we can actually combine these two numbers. 2 minus 1 is just a positive 1. And now what we're going to do is we're actually going to expand this out. Just basic distributive property. When you do that, first, you are multiplying n ones by 10 to the power of n. That's the same thing as n ones, followed by n zeros. So there are n zeros over here. And do you see how we can finish this problem off? By the distributive property. So that was the first operation, and then we have plus n copies of 1 multiplied by 1. Well, that's just going to be itself, but notice how it has lined up perfectly like this. And now, what do we have? If you remember, at the start, we want to show that we could go from here to here. So we need 2n copies of 1. Do we have that when we add things up column-wise? So it's kind of bugging me that this thing starts on a new page. So I'm actually going to move all of this. Maybe give myself more space. In the document, let's just move this down a little bit. But indeed, when we add everything up column-wise, we have n1s and n1s that all line up perfectly. So we have the first n1s followed by a second group of n1s, where we have no carryover because all of these are zeros. Zeros and ones do not carry over. So just to really clarify, in the end, we have 2n copies of 1, which is exactly what we wanted to show at the start. So, congratulations, that's the proof. And now we go into our final problem of this section. This problem will use a little bit of combinatorics. So for those who requested both number theory and combinatorics, well, here's a great problem that I've chosen which has some overlap. Specifically, the pigeonhole principle. That's your big hint for this problem. Show that for any number n that ends in 1, 3, 7, or 9, there exists a rep unit. So this is an existence problem. So there exists a rep unit that is divisible by n. Okay, so the way we're going to tackle this problem is we are going to consider the following list of n plus 1 rep units, and I'm going to list them all out as follows. So let's consider this following list that goes like the first rep unit, the second rep unit with 2 1s, 3 1s, and this list will just continue until the n plus first rep units, which means there are n plus 1 1s repeated. And this is where the pigeonhole principle comes into play. So we have n plus 1 rep units, but remember, when you divide by n, there are only n possible remainders. So let's write that out. By the pigeonhole principle, or the box principle, among these n plus 1 numbers, there must be 2 of them with the same remainder upon division by n. So if you're struggling to see this, let's list out, when you divide by n, the possible remainders are 0, which happens when you are a multiple of n. That's how you get a remainder of 0 when divided by n. You could leave a remainder of 1, 2, all the way up to n minus 1. These are the possible remainders upon division by n. So let's write that out. And let's actually be more specific. That's n possible remainders. So if we have n possible remainders, but n plus 1 numbers in this list, that means 2 of them have the same remainder when they are divided by n. Because we have n plus 1 numbers, but only n possible remainders. Okay, if 2 of them have the same remainder when they're divided by n, that means their difference will be divisible by n. Right? You can think of it, if they both have a remainder of, let's say for example, 2, then when you take their difference, it would be the same as saying basically 2 mod n subtract 2 mod n, which is the same as 0 mod n, so you're divisible by n. Let's start that on a new page. So we'll take 2 rep units and their difference is divisible by n. Now when we take their difference, so the difference of these 2 rep units, which have the same remainder upon division by n, it will have a very specific form. So it will look something like A multiplied by B, where A is a rep unit and B is some power of 10. So if you don't follow along with this, don't worry, we're going to see an example of this later on, but I just want you to know that this is the general form that all these numbers will have. And this is important to write it like this because now we can deduce something very important about these numbers in relation to n. So remember, n is defined as any number that ends in one of these 4 digits, 1, 3, 7, or 9. And the important thing about these numbers is that they are relatively prime to 10. So numbers ending in 1, 3, 7, and 9 are all relatively prime to 10. So their GCD is 1. So therefore, the GCD of B and n is also equal to 1. Because B is some arbitrary power of 10, so it will always be relatively prime to n. Doesn't matter how many times you raise 10 to a power, they're not going to share any common factors with n. Now remember, we said that the difference between these 2 rep units is divisible by n, and it has this form. That means this form is congruent to 0 mod n. But since we've already determined that the GCD of b and n is equal to 1, so in other words, b is not divisible by n, that means this must be divisible by n. So let's erase this part actually. Excuse me. There we go. And so a must be divisible by n. So if you followed along at the beginning over here, so all of this, and then from here all the way to the end, congratulations. Now let's go over this step. Going from this part of the solution to something like this, because this may be a little hard to see, and the best way to do that is to just play around with an example, and you'll see exactly what I'm talking about. So I'm going to give myself some more space. Let's take a look at why the difference between these two rep units will look like another rep unit times a power of 10. And the best way to do that is just to pick an example. So the example I prepared to show you all, and I highly recommend you choose a different number at home, but the one I've chosen is n equals 17. So when n equals 17, that means our list will look like 1, 11, 111, all the way to 1 repeated 17 plus 1, so 18 times. Now, I'm not going to write all of that out. Instead, we're going to use the R notation. So recall earlier on in the document, R1 equals 1, R2 equals 11, and Rn basically just is the number of times a 1 shows up. Okay, that's the notation I'm going to use. So when we have this example, n equals 17. So there are 17 possible remainders. Let's first remember that. Upon division by 17, you could either leave a remainder of 0, 1, 2, all the way up to 16. And since n equals 17, that means we have 18 rep units to examine. So I'm just going to speed this part of the video up. Okay, so I've just written all of that out, and now I've already done some work off to the side so we can save ourselves some time. Underneath each rep unit, I'm going to write the remainder upon division by 17. So I've gone ahead and put this into an online calculator, so I got all of these very, very fast, because as you can imagine, this number is pretty big, so it gets pretty crazy. So this is the remainder when divided by 17. Okay, there we go. So as we can see, in our first 18 rep units, so of the 18 rep units in this list, we can see these are the remainders upon division by 17. And what do you know? Indeed, rep unit 1 and R17 both have the same remainder when divided by 17. So let's take a look. We need to take a look at their difference. And in this case now I do have to write out this rep unit 17 times just to show you how it looks like. So that's R17, and then we subtract a 1. And again, going back to the main concept of just doing everything slowly, column-wise, we're going to see we end up with a number that looks something like this. And then a 1 and a 0 at the end. So do you see how that lines up with something like this? Because this is equal to basically a rep unit times, in this case, a 10 to the power of 1. And specifically, it's equal to rep unit 16 times 10 to the power of 1. So make sure you see how we get this form. See how it's of a form rep unit times power of 10. As we said before, the GCD of 17 and 10 is 1, which means, oh, and I forgot a very important part, because rep unit 17 is congruent to 1 mod n and rep unit 1 is congruent to 1 mod n, this should be congruent to 1 minus 1, which is the same as 0 mod n. Oh, in this case, n is 17. So it should be congruent to 0 mod 17, so it has to be divisible by 17. Now the GCD of 17 and 10 is 1, which means 17 is divisible by R16. So indeed, there exists a rep unit that is divisible by n. In this case, it would be rep unit 16. And we can even get confirmation here. Rep unit 16 is indeed congruent to 0 mod 17. And you can even look back earlier in the document where I list out the first 20 rep units. You'll see 17 is a prime factor of R16. So indeed, this is divisible by 17. So we have found, in the case of n equals 17, indeed, there does exist a rep unit divisible by 17, and it's called R16. Now, there's nothing special or fancy about the number 17, so long as your number follows these conditions, so it ends in either 1, 3, 7, or 9, we can be 100% certain by this procedure the existence of a rep unit that is divisible by n. So indeed, there will always exist a unique rep unit divisible by n. And I think that's a pretty cool, fancy problem to end off on, using some overlap with combinatorics, the pigeonhole principle. We consider possible remainders, and we use a little GCD action, and even an example, and going back to our big concept of breaking things up and doing subtraction column-wise. So I think that's a lot of concepts basically packed into one problem. So that's a good place to end off. And yes, now you have homework. So a little bit longer. I gave you 4 problems this time, and it stretches off into the next page. So this is what I'm leaving you off with. I would say the problems start from medium-ish difficulty and then progress to much harder. And don't feel bad if you can't do these, because especially, I will tell you right now, question 4 is hard. This one is the hard one, marked with a star. But you can see we have something like 1c is very similar to what we did on the question where it says divisible by 41 if and only if n is divisible by 5. So it's basically the same concept, just with different numbers. And I'll leave you to have fun with 2 and 3. 2 is a lot easier than it looks, I would say, and question 3 is a lot harder than it looks, I would say. So I'm going to leave you off with that, and I hope you learned something new today. I hope you learned about this fancy number called the rep unit. It's a very fun area in number theory. I had a lot of fun presenting this concept to you guys, and I hope you can take something away from this lesson and go and solve many problems involving the repeated ones. So that's it for this video. Please leave me a like if you enjoyed, and let me know if you want to see more videos on number theory in the comment section below. And if you have a specific topic that you want me to cover, just let me know and I will put that down in my ideas for future videos. Okay, so with that all out of the way, that was the video. I hope you enjoyed, and get solving. I'll see you in the next video. Bye.